All right, here it is, Wednesday, the 7th of April, and we are going over L'Hopital's rule, which sort of ends. This is the end of graphs and graphing. So when we talk about end behavior of a graph, we're really talking about what happens at plus or minus infinity. And so this begs us to take limits. Okay, so here's one of my favorite examples. We're going to let f of x be the function x over e to the x. Okay? And what we want to do here is compute the limit, because we want to know what happens at the end, right? So we compute the limit as x goes to infinity of x over e to the x, right? And we know the quotient of the limit is the limit of the quotient, so this is going to be, so the limit as x goes to infinity of x is infinity. And the limit as x goes to infinity of e to the x is also infinity. Now, unlike other numbers, this is not equal to 1. You can't do that. And that's because, believe it or not, there are different sizes. There are different sizes of infinity. Some infinities are bigger than others. So, sticking with this example, let's think about this for a second. X goes to infinity at a rate. E to the x goes to infinity at a much faster rate. So eventually, as we go way out to 20-digit numbers, x is much smaller than e to the x. And so this quotient gets closer and closer to 0. And here's the key. That's because the rate at which e to the x goes to infinity is much faster than the rate at which x goes to infinity. And so the bigger number wins, you get 1 over infinity, which is 0. And so what we want to do now is compare rates. And this brings into account this rule called L'Hopital's rule. Now there seems to be differing opinions on how his name is spelled. He was a French mathematician. And some people write it like this. Sorry. Some people write it like this. Like hospital. And students tend to like this because when they use L'Hopital's rule, they say call the doctor or whatever, but our book writes it like this. That's the way I've always seen it written. So, and here's what it says. It says if, so it's a theorem, if the limit as x approaches, I'm going to use infinity for now, but we can I'll put the c here. If the limit as x approaches infinity of f of x over g of x equals infinity over infinity, and you can have pluses and minuses in there, or 0 over 0, then the limit equals the limit of the derivatives. Right? So in the first move, so here in move 1, you see that it's infinity over infinity, or 0 over 0. And you go, okay, which one's going there faster? So you take derivatives and you compare the rates, which is what a derivative is. Okay? And if this gives you a number, say 5, then that's the limit. If you get infinity over infinity or 0 over 0, again, you can keep doing this as many times as you want, okay, until you get an answer. And it could be that you get 1 over 0 or infinity over 1. These are just numbers. Both of them turn out to be infinity. But as long as you keep getting infinity over infinity or 0 over 0, then you keep using L'Hopital's rule. So here we go. So here's the example again. Take the limit as x goes to infinity of x over e to the x. We get infinity over infinity. And then you go like this. You go, so this is equal to, and you always put an LH here to tell me you're doing L'Hopital's rule. The derivative of x is 1, and the derivative of e to the x is e to the x, and that's 1 over infinity, which is 0. And this also tells you have a horizontal asymptote at y equals 0. So what's important to note here is that infinity over infinity and 0 over 0 are called indeterminate forms. 0 over 0 is not 0 or 1, and infinity over infinity is not 1. It's undetermined or indeterminate, right? So these are indeterminate forms. There are some other ones. We're only going to do 3 of them, but there's a whole bunch of them. There's a whole science to this. So the third indeterminate form is infinity times 0. We'll look at that. A fourth one is 1 to the infinity, which is not 1 or infinity. And a fifth one is 0 to the 0. All of these require more work. The two biggies, though, are this guy, because this allows you to use the L'Hopital's rule. Okay. That's it. That's really the whole lesson. If you get infinity over infinity, take derivatives. Oh, and this is note, or this is key. So if you have this, I'm just going to use infinity over infinity. It could be 0. Okay, and then you use the L'Hopital's rule. It's f prime of x over g prime of x. So you're comparing the rates, so you take the derivative on top, you take the derivative on, this is not the quotient rule. You're not taking the derivative of the whole thing, you're taking the top derivative here and comparing it to the bottom derivative. So you're not doing the quotient rule. That's the big mistake that people make. It's much easier than that. The quotient rule is hard. Okay. So here's another example. What's the limit as x approaches 0 of sine x over x? The sine of 0 is 0, and 0 is 0, okay? So use the L'Hopital's rule, and you get cosine of x over 1, and the cosine of 0 is 1. So there's the limit. So even though the function is undefined there, the limit is defined. Okay, here's another one. We're going to take the limit as x approaches 0 of the square root of 1 plus x minus 1 over x. And this has to come from the right, not a big deal. Okay, when you plug in 0, you get 1 minus 1 over 0, which is 0 over 0. Okay, no, by L'Hopital's rule. This is 1/2 1 plus x to the minus a half over 1. The derivative of 1 is 0, and the derivative of x is 1. And this becomes 1/2. Okay. Here's another one. The limit as x approaches 0 of 1 minus cosine x over x plus x squared. This is 1 minus 1 over 0, which is 0 over 0. All right. And then we get, let's see, the derivative of 1 is 0. The derivative of minus cosine is sine. And then you have 1 plus 2x. And that's 0 over 1, and that's 0. Okay. All right, so, you know, if it's infinity over infinity, 0 over 0, use L'Hopital. We're going to talk about this guy, because it really is just one of the other two. You just haven't, you can't see it. So I'll use one of my favorite examples. We've looked at this in class, but I didn't tell you what was going on. If you take the limit as x approaches 0 from the right of x times the ln of x. So when you plug in 0, you get 0 times minus infinity. Right? So we have this indeterminate form. Oops. Don't want that to go away. So it's 0 times infinity, which isn't 0 and it's not infinity, it's indeterminate. So what we do is you do a little algebra trick. Everyone's favorite word. I'm just going to rewrite this thing upstairs here in a very clever way. Right? X times ln of x is the same as the ln of x divided by 1 over x. So it's just an algebra trick. And so, okay, this gives us infinity over infinity. Actually, minus infinity, sorry. Doesn't matter. Okay, now you use L'Hopital's rule. The derivative of ln of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. So this becomes minus the limit as x approaches 0 from the right of 1 over x times x squared over 1, which is minus the limit, and that is 0. Okay? So the limit exists. And we actually fiddled with this function in class. If you go to graph it, I think there's a we showed there's a minimum at 1 over e, like right here, and this thing comes off here at 1, and then as it comes back to the asymptote here, the limit coming from the right says that it goes to 0, and that's from this limit right here. So that's what that guy looks like when you graph it. Okay, easy, pretty easy section. And I will see you in a minute for some guided practice.